Would you believe me if I told you that analysis of complex beams is easier than you think? This is with the help of qualitative analysis. Qualitative analysis uses simple calculations and intuitive understanding of structures to analyze structures without need of any complex calculations. This lecture is part of my video series on IStructE certificate in structural behavior. So if you are preparing for this exam, or if you want to understand basic behavior of structures, this video is for you. Let's dive straight into our lecture today. Here my main focus will be on sketching bending moment diagram. Bending moment diagram is one of the key skills that every structural engineer should have. It helps us where loads are going in a beam so that you can provide reinforcements accordingly, either tension or compression in a reinforced concrete beam, and you can analyze and design properly any steel beam as well. This is the question where I will be trying to find out the bending moment diagram. But before I solve this question, I will give you a full background to analysis of complex beams, which will really help you to clarify your basic principles of structural analysis. These are the 4 options for this question. What option is the correct one? Just test your knowledge before watching this lecture. It will help you think about structural analysis. You can scan this barcode or go to this URL, link will be down in description, to try this question first. Pause this video now and try to find the solution to this question. But this lecture is not only limited to this question, but the larger perspective of how do we analyze complex beam will be covered in this lecture. First, let me talk about background to complex beams. And here I will consider 3 things: external moments, distributed loads, and pins or hinges. When we have these things inside a beam, the complexity increases and it becomes a bit difficult to analyze as compared to simple beams where you just have supports and loadings. In this case, external moment is applied at B, and you can see the pattern of bending moment diagram over here. Tell me one thing, where do you think there will be points of contraflexure? Points of contraflexure are the points where bending moment diagram changes sign from negative or hogging to positive or sagging moment, or where deflected shape changes the curvature. This is often very misunderstood concept in this scenario. Here you can see when we apply moment which is clockwise at B, it develops a resisting moment. It is not changing at all throughout the span. It means that there is no point of contraflexure over here. Before I go through analysis steps, I would like to cover some basic rules for qualitative analysis. Basic understanding of these golden rules, what I call as golden rules, is really very crucial for understanding this topic. Firstly, the bending moment is always 0 at simple pin or a roller support. Here you can see point A will have 0 bending moment. Other points B and C, they have moments, but this is due to continuity between 2 spans. Rule number 2 is about bending moment diagram crossing the baseline. Wherever it crosses the baseline, wherever bending moment is 0, it is termed as point of contraflexure, or in other words, we call it as inflection point as well. At that point, bending moment crosses the baseline from hogging or negative moment to sagging or positive moment. At that point, bending moment is 0. Here in this case, when we have a propped cantilever, when a point load is applied, The curvature is being changed over here for deflected shape. Wherever bending moment diagram changes sign, it is termed as point of contraflexion. Let me now move to third rule. The bending moment diagram under a distributed load is always parabolic or curved. Here you can see that it is straight up to this point, and then from here onwards, as you have UDL over here, the bending moment diagram is curved. It is not a straight line. So remember, for distributed load, bending moment is always curved. The diagram is always curved. Let me move to golden rule number 4. Whenever you have a fixed joint, when you are applying loading at the other hand, this end which is fixed, it will not rotate at all. This is the basic condition of a fixed or a built-in or encaster joint, is that it will not rotate at all. In this case here at A, it is not rotating at all. Rule number 5 is that whenever you have point loads, the bending moment diagram is going to be straight line. So there will not be any curved portions in the diagram. A point load is applied here, which is creating straight lines, and it can be viewed over here as well, that these are straight lines. Golden rule number 6, and I assure you this is the last one and we are done with the golden rules. It says that if part of a structure remains straight after loading, no bending moment develops. In this case, when we apply loading, here portion between C and D, it is literally straight portion. Because of a roller support, the bending moment is not being transferred to the other side. It's not being transferred to D. That's the reason at point C, we have zero bending moment. The bending moment ends at this point. Let me just remind you support reactions. When we have a roller support cannot move in vertical direction. It will only have vertical reaction. However, in terms of deformations, it can rotate and it can move in horizontal direction. A pin support or hinge support can be taken as a door. So imagine a door. You can always rotate a door, but it cannot move in upward direction. It cannot move in horizontal direction. Wherever it cannot move, it will have reactions. It will have horizontal and vertical reaction. How about the fixed support? In case of fixed support, everything is fixed, tied together. A beam cannot rotate. A beam cannot move in horizontal direction, and it cannot move in vertical direction as well. So these are the basic support conditions that you need to remember in order to analyze a structure qualitatively. I had to consider 3 points: moment loading, distributed load, and hinges or pins. So let me start with the first one, which is moment loading. When moment loading is applied to a beam, what it will do, it will try to put one portion of the beam in tension. So one portion will be tension at top and other portion will be tension at bottom. External moment has this kind of effect. Here, when you are trying to apply a clockwise moment, portion between A and this point where moment is applied, it will be tension top and compression bottom. And this portion that you see between the point and B, that will have tension at the bottom and compression at top. These are the 3 steps that I was talking about, that I will tell you 3 steps that you can use to plot not only bending moment diagram, but find out the deflected shape and find out the direction of arrows. Once you have direction of arrows, then you can literally find out any member forces. You can find out shear force as well. You can find out bending moment. You can find out axial forces. So these 3 steps are: first, we have to find out points of certainty. What are points of certainty? These are the points where deflected curve or shape must pass through. And there are a couple of things here. One is that it must pass through the supports. And second is that wherever you're applying a point load, it should pass through point load as well. Or if you're applying distributed load, it should pass through the maximum distributed load. When we are applying moment at this point, it is causing it to move downwards, and this portion will move upwards, and points of certainty are this left support and right support, and must pass through this point as well. Second is deflected shape or deflected form and direction of reactions. When you apply moment here, see that this portion between A and point of application, it is going up. That means that tension is at top and compression at bottom. On the other hand, here between point of application and B, it is going down or it is sagging. It means tension bottom, compression top. When this is going up, imagine if you don't have this support B, then this will go straight up. To bring this one down, I need a downward reaction. That's the reason you will have a downward reaction at A in this case. And to balance this downward reaction, you will have upward reaction at B. Once you've got direction of reactions, then you can plot shear force diagram, you can plot bending moment diagram as well. Next step is to plot bending moment diagram. And here, wherever you are applying external moment, unless if it is the end of the beam, if it is at any portion along the beam, one side will always go up and other side will go down. Here we applied a clockwise moment. If the moment was anti-clockwise, then this portion on the right will go up and the portion on the left will go down. So it is just trying to rotate anything. So just if I'm trying to rotate this, it will rotate. If I had a flexible ruler, I would have shown you how it can be done. I have got one, but it is at my workplace, so I forgot to bring into this home studio. The second point is distributed load. What happens when we apply distributed load? And the effect is pretty obvious. When we apply distributed loads, then sagging will happen and bending moment diagram will be curved. It will not be a straight line anymore. So if it was a straight line here, distributed load is applied only on this central portion. When we apply loading, the end moments will be like this, but the portion between the start of UDL to the end of UDL, it will be curved. The other portion will be straight lines. The moment between line connecting these 2 points, it will be WL square over 8. Whenever you are performing approximate analysis, you can find out moment by saying that it's WL square over 8. That will be approximate moment on a beam without carrying out any calculations. At least it will give you some kind of flavor of what moment is being developed over here. Some other examples of distributed load, partial distributed load that is on this beam. If the overhang portion in this case is nearly equal to portion which is inside, then in this case you will have negative bending moment here and then positive will go down. But if the overhang portion is quite a lot, then deflected shape will look like this, and here at A reaction will be downwards. In this case you will have negative bending moment or hogging bending moment for the entire structure. If the loading is really very heavy, or if the span is quite a lot as compared to a span inside the beam, then entire moment is going to be negative. This is an example which I have taken from IStructE Essential Guide on Approximate Analysis of Structures by David Braun, and I will give a reference at the end. Here you have in situ reinforced concrete slab. On top of that slab, the entire portion of precast concrete is resting, which means that there will be heavy moments at this point. It was a requirement in this project, which was an office building, to leave this space column free. Now this is developing entirely hogging moment. Hogging moment means negative moment. And what are the design implications? The detailer gave area of steel at top and area of steel on this side as well. The normal situation is that you will always have negative bending moment here, and then you will have positive bending moment at this point. So what detailer did is he or she provided the hogging reinforcement there, and then a positive reinforcement here, which is not needed. We need heavy negative or hogging bending reinforcement over here. So this was miscommunication. Imagine if this would have been built, it would lead to a disaster. So wherever you have bending moment, you provide reinforcement at that point, because reinforced concrete, it cannot take any tension. So wherever you have, especially when you have tension, almost certainly you will need steel reinforcement so that it can work together. So previously you saw that here that the bending moment is developing over here, which is entirely negative. That means that all reinforcement should be provided over here, and this reinforcement is not necessary. Then I will move to the third point, which is pins or hinges. Why do we need hinges or pins? Mostly in steel buildings, we need pins or hinges in two cases. One, in steel structures, most of the time joints are pinned and we need bracing to resist lateral loading or wind loading or earthquake loading. Here, this is the example of bracing. This is connected with pins over here, and all joints are pinned. In most steel structures, 99% of the time, we have pinned joints or hinges, and to resist lateral loading, we need bracing. Another very good example is in precast construction. In precast construction, most of the time joints are pinned, because even in precast bridges, you will see that precast beams, they are placed on bearings, and where there's a gap between two beams to allow rotation. Remember, when rotation is allowed, it means that it is a pin. When rotation is fixed, that means that it is a fixed joint. So two cases: steel buildings where joints are pinned, we use pins, and in precast construction where rotation is allowed, joints are pinned. Additionally, we also sometimes need pins to reduce a structure from statically indeterminate structure to statically determinate structure. Here in this case, just to simplify the analysis and also to reduce the cost of the frame, because remember that when you have a fixed joint, especially in the steel frames, it costs a lot and fabrication cost increases, and in buildings especially, 50% of the cost of the frame, it comes from joints or fabrication. Here, the left frame is statically indeterminate to first degree. Statically indeterminate structures are the structures where we have redundant members or extra members, which we cannot solve using ordinary equilibrium equations, where stiffness matters, which means that thicker, heavier sections are going to take more loading, more moment, more shear force. In case of statically determinate structures, geometry defines the load distribution. So stiffness does not really matter. So if you have one member which is really very heavy and one other member which is skinny or thin, they will take same loading because it's controlled by geometry, how they are connected, what is the geometry. While here, in case of indeterminate structure, heavier members will take larger forces. So SI, static indeterminacy, is equal to 3m plus r minus 3j. 3m means there are 3 forces in a rigid frame. 3 times these 4 members is 12 plus 4 reactions. We have pin joints minus 3 times j. Joints are 5. 1, 2, 3, 4, 5. It gives us SI is equal to 1. When we introduce a pin over here, then you will see that one force will be released from here, which will make this structure as statically determinate structure, which is easier to analyze. You do not need any computer, just do the hand calculations. That's it. So this is another use of pins. Here again, in this prop cantilever beam, a hinge will make this a determinate structure, and it is one of the key analysis skill as well. So wherever we have points of contraflexure, we assume there is an internal pin, and then it makes our life easy in terms of analyzing a structure. As I mentioned, the hinge is always a point of contraflexure. It means it will have 0 moment. Here we have this hinge, and this is acting as point of contraflexure, which means that it has 0 bending moment. And we can use this single concept to analyze little bit of complicated beams and find out its member forces, at least approximately. Now here again, I will apply 3 steps. Points of certainty, where deflected shape will pass. Secondly, deflected shape and reactions. And thirdly, I will find out bending moment. Here we have internal pin. When we apply loading, there's a little bit of slope discontinuity over here, but again the slope maintains and it reaches over here. So this is the deflected shape. Due to this deflected shape, what we can do, this is going up, so the reaction will go up, and again here reaction will go up as well. The load is creating anti-clockwise moment with respect to fixed joint. This means that resisting moment will be clockwise. This point load is creating anti-clockwise moment with respect to fixed joint. Therefore, the resisting moment will be opposite to that, that is clockwise. Once we have got this, then we go to third step, which is bending moment diagram. As we have a clockwise moment at the right side, remember clockwise moment at right side will always generate, if you apply clockwise moment at right, it will always generate hogging. If you apply clockwise moment at left, it will generate sagging. So here hogging moment is generated, and when we apply downward force, it will generate sagging moment. So that's why this bending moment diagram is coming down over here. And then simply there's nothing in between these 2 points, so we connect it with a straight line, and there's nothing between A and where load is applied. We connect these points. We can isolate pin as well and see that how shear force is acting. On the left of the pin, shear force will act upwards. The reason is that because the load is downwards. And on the right side, because the reaction VC is upwards, so the force in pin will be downwards. It is really very important to remember. It will help us analyze lots of complicated, complex beams really very easily. Imagine this structure is a reinforced concrete structure, and the hinge will be formed by making 2 halves of the joint. And here this is the hinge, and you have 2 options to choose from. Which option is correct here? Think about it and put your option down in comments and say that you are solving this reinforced concrete structure. Now here, see that we have a roller support over here. On right side we have a fixed support. So right side is going to be stronger. So that's why left side should be placed on right side, because naturally it's the correct choice, isn't it? And for B, you can see that right side is resting on the left side. And if this is the case, then this is rotating and this pin is rotating as well. It means that this is not going to take any loading at all. So B is incorrect. Option A is the correct one. Did you get it right? Okay, let's move on. Whenever you see a hinge, you have to establish if neighboring reaction is 0 or not. Here in this case, when we are applying loading, the hinge is rotating this part, point E, and there should be something to take into account over here to make it work. But because when we are applying loading, this is rotating and this is rotating as well. So when this is rotating, it will not develop any moment beyond the loading point. If it was a fixed support here, the situation would have been different and it will develop some moment. However, in this case, because rotation is allowed at the end, a pin will not transfer any moment to right. So here neighboring reaction is 0. This is one of the interview questions as well. If somebody asks you during job interview that what will be reaction at E, don't just start calculating and using moment distribution method to find out reaction. Just use your intuition, use common sense, and use basic knowledge of the structural engineering to find out reaction very quickly. The hinge is in such a position as to allow reactions to be created at each support. When we are applying loading over here, in this case, this is the point of certainty and we have hinge over here. When we apply loading, this portion is deflecting downwards and the portion over here it's deflecting upwards. To understand the distribution of shear forces, you can introduce artificial member at a point where you have hinge, and that it will give you a real flavor of where the loading is going. And again, finally, we plot the moment diagram like this. Because it is going down, it will be sagging, and at this point C, because of continuity, you will have hogging moment. Because this reaction is downward, so downward reaction is going to create sagging at the fixed end. So that's why it is in sagging. Now let me move to quiz question, the actual question. What is the correct bending moment diagram for this case? We have 4 supports and loading is applied at outer spans. There are 4 options to choose from. I'm not sure what option did you come up with, but you will see in a minute that what answer is right. So again, I will apply these 3 steps. First, point of certainty, where deflected form or shape has to cross through. And here these points are these support points and the loading points. So these are the points where deflected shape should cross. Do you agree with me? All right. Okay, then I move to the second one where I will plot the deflected shape. Now, this has made my life a lot easier because all I have to do is just to cross a dotted line and that will make it deflected form. So here, when you push it down and push it down at the ends, the middle portion will go up. It means that here we have tension at top, here tension bottom, tension bottom. Tension means stretching, compression means squashing. First, we need direction of reactions. Because of downward loads, all reactions are going to be upwards. Thirdly, we have to plot the bending moment diagram. And this deflected form is going to guide us hugely in terms of coming up with the right bending moment diagram. So they all go hand in hand, direction of reactions, deflected form, and bending moment diagram. So first, it will come down here. The reason is that load is being applied. And secondly, at distributed load, we will have a parabola or curve, and it is passing through some point over here, which is called point of contraflexure. The reason is that we have continuity over here. Then between these 2 points, we don't have any loading at all. And now we can connect these 2 points as well to complete the loop. Once it's done, we can rub off the deflected form and we can shade this diagram to make it look really beautiful so that it's pleasant to your eye. Did you understand it now? Okay, let's move on. So the correct answer is option D. I will go back to the options again. Here, option A is incorrect. The reason is that there is no continuity, so the moment will go somewhere. This is incorrect as well because due to continuity, you will have some hogging moment over here, which is missing. And again, here you don't have any hogging moment over here, which should be the case. You should have hogging moment. So the correct option is option D. Once you have completed these problems, then there are homework problems as well. So use these homework problems to find out deflected shape, reactions, and bending moment diagram. For preparing these lecture slides, I've taken references from these 2 books. Feel free to have a look at these books. You can have access to this entire video series by going to this URL or scanning this barcode. So scan this barcode to have a look at all lectures which I've been preparing on qualitative analysis of structures. You can download the lecture slides by going to this URL or scan this barcode. So solve it as you move on, as you watch video. It will really help you. Thanks for watching this lecture today, and I will see you in my next lecture. Thank you.